Welcome. This video is CCBYCN. Welcome back, everybody. We are to the third section in chapter 5, which is the law of signs. Law of signs is a bit more complicated, and I'm going to actually show you where everything comes from. If we're given an ABC triangle, like our typical triangle here, and I drop this down as the height, then it splits it into two separate triangles. Again, what we're trying to do is solve any triangle, whether it's a right triangle or not. And in this case, we're going to assume that it's not a right triangle. If it is, then it's much simpler, of course. I'm going to notice that when I look at this small triangle here, we have that the sine of angle A is equal to H over side C, which means that H is equal to side C times sine of angle A. Also, if I look at the bigger triangle here, right triangle, I have that the sine of angle C is equal to the opposite, which is H in this case, over side A, which means that H is equal to A times the sine of angle C. And the point here is that this is equal to H, and this is equal to H. Have to imply that C times the sine of A, angle A, is equal to side A times the sine of angle C. And we can rearrange this as the sine of A over side A is equal to the sine of C over side C. And that is the essence of the law of sines. Now we could do this again and end up where sine of B, angle B, is over side B. So our summary here is that the sine of angle A over A is equal to the sine of angle B over side B, which is also equal to the sine of angle C over side C. And this is the law of sines. Some books may write this differently, where everything's flipped upside down, where you have the side over the sine of the angle, but it really doesn't matter. Everything ends up being the same anyway. Now, we only use this when we have angle, angle, side, or, and this is the bigger deal, when we have SSA. Side, side, angle. And I'll talk a lot more about that in a few minutes, but we're going to start with angle, angle, side like we have here. And we'll start with the triangle, ABC. A, B, and C. And we have that angle A is 102 degrees. We have that angle C is 33 degrees. And that side A, that's the side opposite angle A, is 20. And when they say solve the triangle, what they mean by that is find all the missing sides and angles. So we're looking for this angle, this side, and this side. And then we will have solved the triangle. Let's start with the angle. That's going to be the easiest part. So angle B is going to be 180 degrees minus 102 degrees minus 33 degrees. Because the sum of all the interior angles of a Euclidean triangle is always 180 degrees. So let's do that. 180 minus 102 minus 33. So our missing angle B here is 45 degrees. So there's our first part of that. Now that I know that, I can actually do the law of sines. I'm going to notice that I have, and what I need with the law of sines, of course, is an angle, a known angle with its known opposite side, which we have with A here. We have the angle 102 and the opposite side of 20. That's going to kind of be my base, as it were. So this says, using law signs, that the sine of 102 degrees over its opposite side, which is 20, is going to equal, I'll say, the sine of 33 degrees over side C. Well, I can cross multiply and divide. I end up that C is equal to 20 times the sine of 33 degrees over the sine of 102 degrees is, now again, I'm going to obsessively double check that we are in degree mode. If you're in radian mode, you'll have to switch it. We have 20 times the sine of 33 degrees divided by the sine of 102. Now we have side C. 11.136, we'll say. And we do not have a unit with this. Now I'm going to do it again. I'm going to say that the sine of 102 degrees over 20. Now I'm going to use my new angle B, the sine of 45 degrees over side B. And once again, I'm going to cross multiply and divide. I end up with B is equal to 20 times the sine 45 degrees over the sine of 102 degrees. So 20 times the sine of 45 divided by the sine of 102. And that is how you solve a triangle using the law of sines. Let's do another one. This one is also angle, angle, side. And let's draw a triangle just to make sure. And angle A, B, and C. They tell us that angle A is 56 degrees. Angle B is 65 degrees. And side A is 12. So there's our base again, angle A and side A. We have the angle on the opposite side. So let's find the missing angle, which is angle C. That's going to be 180 degrees minus 56 degrees minus 65 degrees, which gives us 180 minus 56 minus 65. Now, those of you watching this video, you should be pulling out a calculator and doing this calculation in your calculator with me. Pause the video if you need to, whatever you need to do. That gives me 59 degrees. And we'll use that here in just a second. So now I'm going to use the law of sines. So this is 59 here. And we're missing side B and side C. So the sine of 56 degrees over its opposite side, which is 12, equals the sine, I'm going to do 65 degrees over its opposite side, which is B. And we're going to cross multiply and divide. We end up that B is 12 times the sine 65 degrees over the sine of 56 degrees. Degree mode, 12 times the sine of 65 divided by the sine of 56. Looks like we're getting 13.118. Oh, here's our first answer. Second answer is here. And now for the missing side C, we have the sine of 56 degrees over 12 That's my standard there. And now it's going to be the sine of 59 degrees over side C. We cross multiply, divide. We get 12 times the sine 59 degrees over the sine 56 degrees. Times the sine of 59 degrees divided by the sine of 56 degrees. And we get 12.407. Not too bad. You just need to have an angle and the side opposite of it known somehow before we can apply the law of sines. All right, so now we're to the kind of big deal. The ambiguous case of the law of sines. Here's the thing. Because sine is positive in both quadrants 1 and 2, we can end up with an ambiguous case, meaning given some information, we may end up with two different triangles with the same original information. This only happens when we get a side-side angle. And the kind of joke is, it's easy to remember because you need to watch your ass, right? You got the ASS is the case where you have to really take a step back and go and look for that extra potential angle that may exist there. That's a little bit more difficult to verbalize, so I'm going to write it out and show you what I'm talking about. In example 3 and 4, we'll show that. This one says that we have that A is 48, side B is 69, and angle A is 29 degrees. All right, so what we are missing are angles B and C and side C. And we'll get to all that. All right. So I can see that I have an angle and its opposite side. So that's I'm gonna use that. So the sine 29 degrees over 48 is gonna equal, and we're gonna do B here. The sine of angle B over 69. And here's where the problem comes in. This is going to be 69 times the sine of 29 degrees over 48. All right. Now to get angle B, I need to keep in mind that when I do inverse sine to this, I get two potential answers. So in degree mode, inverse sine of 69 degrees times the sine of 29, make sure you close your parenthesis, divided by 48. And here we get this. And we'll store that into memory A. So 44.18, we'll say degrees. That's in quadrant 1. We know that. Here is the problem. Use the space here. Angle B, 44.18 degrees, is here. There is another potential angle here. Meaning this angle. And the way that I'm going to get that angle, the red angle, is I'm going to do 180 degrees minus the 44. Put this on A. So I'm going to go 180 degrees minus angle A. So the red angle here is the 135.8 degrees. Store that as B. The store button, once again, is down here. Hit store, and then you can choose any of the green memories. You just have to hit alpha first. So this is 135.8 degrees. Put that in B. We'll deal with that in a moment. So let's start with the triangle. I'll try to draw it as similar as I can. A, B, and C. We're starting with 29 degrees, 48 here, 69 here. And we are going on the assumption that angle B is 44.2 degrees. That's this one here. Based on that assumption, we can figure out what angle C is. Angle C is going to be 180 degrees minus 29 degrees minus our 44.2 degrees. That's in memory A. And we get that angle C is about 180 minus 29 minus A. Let's store that as C. So I got 106.8 degrees. That's right there. All right. So we have solved part of this triangle. We know that angle B, in this case, is the 44.2 degrees. The only thing that's missing now is side C. That's no problem. Now that I have angle C, we don't have an issue. So we're going to do sine of 29 degrees over 48 equals the sine of the 106.8 degrees, which I'm going to use memory C for that, over side C. Which means that side C is 48 times the sine 106.8 degrees over the sine 29 degrees. All right, so we are in degree mode, so we're going to go 48 times the sine, and the 106 I stored off as memory C. So alpha C equals divided by the sine of 29 degrees. There we go. 94.77 feet or whatever the missing piece there is. All right, next up, what if we have the ambiguous case, the 135.8? Well, let's see what happens there. Triangle again. My triangles are clearly not drawn to scale, so. And we are going on the assumption that angle B is now 135.8 degrees from up here. Well, that's going to give us an angle C of 180 degrees minus 29 degrees minus 135.8 degrees. And that's going to be about, let's see what we get. And of course, for this, I'm going to use my memory B. So 180 minus 29 minus memory B. Now, had that been a negative number, we would say there's no ambiguous case, there's not a second triangle. So we would just be done with the blue. However, because we did get a positive angle here, we now have an ambiguous case. I'm going to store that as D. So we got 15.18 degrees. Okay, so now that we have that, and again, this is the angle that goes right there. And we also have that angle B is about 135.8 degrees. So here's our second correct answer. So now we're going to use the law of sines. Sine of 29 degrees over 48 equals the sine of 15.18 degrees over side C. Cross multiply, divide. We end up that C is 48 times the sine of 15.18 degrees. Of course, I'm going to use memory D for that. Over 48. Over sine, pardon me, sine of 29 degrees. Degree mode, 48 times the sine. That I stored off as D divided by the sine of 29. That is the ambiguous case. We're going to do another one right now. Example 4 is, again, potentially an ambiguous case. They give us that B is 13. Side C is 16. Angle B is 33 degrees. And you can see it's side-side angle or angle side-side, however you want to remember it. And very nicely, we have an angle with its opposite side known. So that's going to kind of be our base there. And we'll see if we end up with an ambiguous case or not. So let's do the sine of 33 degrees over 33 over 13, pardon me. And I'm going to do the sine of angle C is over 16. Cross multiply, divide. I get that sine of C is 16 times the sine of 33 degrees over 13, which means that C is potentially equal to degree mode. So inverse sine of 16 times the sine of 33, close, divided by 13. Make sure you close that parenthesis on that sign there. And here's our 42.09. I'm going to store that as A. And for the same reasons as the problem before, when I did this, I'm going to do the 180 minus that angle, this angle. So 180 minus A. So here's our other potential answer, 137.9 degrees. I'm going to store that as B. And when you store a new memory, it erases the old and puts in the new. And since I don't need those other ones anymore, I can just do that. All right. So let's start with the assumption that C is 42.09. And we'll draw the triangle. A, B, and C. This side is 13. This angle is 33 degrees. This is 16. And we are assuming now that angle C is 42.09 degrees. So C is one of our answers, and we can of course find angle A by going 180 degrees minus 33 degrees minus our 42.09, which again I will use memory allotment A. 180 minus 33 minus A. So A in our case is about 104.9 degrees. That's the angle that goes right there. I'm going to call that memory C. So store as alpha C. All right, now that we have two of the three pieces taken care of, let's find the third by doing the sine of 33 degrees over 13 equals the sine of the 104.9 degrees, which I stored into C, over side A. This means that A is 13 times the sine of 104.9 degrees over sine of 33 degrees. Let's see what we get. 13 times, that is sine of C, divided by the sine of 33. Looks like we're getting 23.065. Let's see what we got. 23.0656. And there's our third piece. That's one potential triangle. Let's see if there's a second potential triangle. Let's draw another with the angle C of 137.9. Now, again, it's possible this triangle doesn't exist. We'll know in just a moment. And we're now going to use, let's pick green. And that is here, 137.9 degrees. Which again, I stored off into memory B. So angle C, in this case, is about 137.9 degrees. Here's one of our three answers for this one. To find angle A, that's going to be 180 degrees minus 33 degrees minus 137.9 degrees. Now, here's the moment of truth. If this is a positive number, then we have a second triangle. If it's a negative number, then we don't. 180 degrees minus 33 minus B. There it is, it's positive. 9.09 degrees. There's our second potential answer. And that angle, of course, is right there. And again, these triangles are definitely not drawn to scale. So we now have that the sine of 33 degrees over 13 is equal to the sine of the 9.09, which I did not store off into D. So let's once again store that to memory D. Over side A, which means side A is equal to 13 times the sine 9.09 degrees, which again, I'll use the letter D for that, divided by the sine of 33 degrees. Let's see what we get. 13 times the sine, I'm in degree mode, 13 times the sine of D divided by the sine of 33 degrees. We get 3.77 as our last side. So that's the ambiguous case. Again, when we do the subtraction, if we get a negative here, then that second triangle doesn't exist. And so we only have one triangle. And that does happen, that does come up. All right, last problem. A pilot is flying over a straight highway. It's a man in this case, he determines the angles of depression to two mileposts, 4.5 kilometers apart, to be 28 degrees and 51 degrees. And you can see this here. So we have a side here. Part A is find the distance of the plane to point A. So we're looking for this distance here. And the second one is find the height of the plane. We'll get to that. Before I do that, I want to find this missing angle here. These are supplementary angles, which means when I add all of them up, it should be 180 degrees. So if I do 180 minus 28 minus 51, I should get this missing angle here, which is 101 in this case. (101 degrees). Now, if you remember your geometry, when we have two parallel lines like this, and something called a transversal, a line that's chopping through it, these opposite angles are always the same. So that means that this is 28 degrees, and that this one is 51 degrees. All right, so they want to know the distance from the plane to point A. We'll call this side B since it's opposite angle B. That is not a problem because this is part A. I have an angle and its opposite side. So this is the sine of 101 degrees over 4.5 is equal to the sine of 51 degrees over side B, with being the distance from A to the plane, which is what we're looking for in part A, the distance from the plane to point A. Rearranging this, B is going to be equal to 4.5 times the sine of 51 degrees over the sine of 101 degrees. So we're in the right mode. 4.5 times the sine of 51 degrees divided by the sine of 101. So the plane is about 3.56 miles, kilometers away from point A. The second part to this, part B, is what is the height? Well, now that I know this, and I'm going to go ahead and store that off as A, this long number here, so store as A. And it looks to me that this, I'll call it H, is the opposite of angle 28. So now we're to a right triangle. That's good for us. So that means that the sine of 28 degrees is equal to H, which is the height, which is what part B is looking for. This is part B. Divided by B, which is the 3.56, and I'll use the memory for that, of course, which means H is about 3.56 times the sine of 28 degrees. Let's see what we get. So once again, I store that off as A. So A times the sine, let's double check it, it's in degree mode, times the sine of 28 degrees. So it looks like the height is about 1.67 kilometers off the ground. I should box this as well. So you can see lost signs can be useful, very helpful in some cases, and I hope that helped.